Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 12 of Differential Geometry. लास्ट लेक्चर में हमने फ्रेने फार्मूला के बारे में देखा था और फ्रेने फ्रेम फील्ड के बारे में पढ़ा था और उसके बाद हमने लास्ट में एक एग्जांपल की थी जिसमें हमने यूनिट टेंजेंट वेक्टर, यूनिट बायनॉर्मल वेक्टर और यूनिट नॉर्मल वेक्टर कैलकुलेट किए थे और फ्रेने फार्मूलाज को हमने अप्लाई करके उस केस में हमने कर्वेचर और टॉर्शन को कैलकुलेट किया था। आज के लेक्चर में हम ये देखेंगे कि फ्रेने फार्मूलाज को यूज़ करके हम कर्व की अप्रॉक्सीमेशन कैसे कर सकते हैं। कोई भी अगर कर्व गिवन हो उसकी हमने अप्रॉक्सीमेशन फाइंड आउट करनी है तो हम फ्रेने फार्मूलाज को यूज़ करके ये कैसे फाइंड आउट कर सकते हैं। उसके बाद हम ये देखेंगे कि कर्व की प्रॉपर्टीज़ को कैसे डिराइव किया जा सकता है। फॉर एग्जांपल अगर किसी कर्व का कर्वेचर कांस्टेंट है तो इसका क्या मतलब है, और अगर कोई कर्व है जिसका टॉर्शन 0 है तो इसका क्या मतलब है। इन तमाम प्रॉपर्टीज़ को हम डिस्कस करेंगे और डेफिनेटली ये तमाम चीज़ें जो है तभी पॉसिबल है अगर हमारे पास फ्रेने फार्मूलाज हैं और फ्रेने फ्रेम फील्ड है। सबसे पहले जिस चीज़ का हम आज के लेक्चर में यूज़ करेंगे वो है कि हाउ टू फाइंड इक्वेशन ऑफ ए प्लेन, और इन अदर वर्ड्स 3D में और स्पेस में और R3 में एक प्लेन है उसको हम कैसे डिफाइन कर सकते हैं। सो हाउ डू वी डिफाइन ए प्लेन। सो ए प्लेन इज डिटरमिन्ड बाय नंबर 1 3 नॉन कोलिनियर पॉइंट्स। सो अगर कोई भी 3 नॉन कोलिनियर पॉइंट्स हैं 3D में तो इट विल डिटरमिन ए यूनिक प्लेन। दैट्स वन थिंग। सेकेंडली I can define a plane by two informations. One, a point on the plane, and the second thing is a line or a vector perpendicular to the plane. So for example, in this picture I have this vector q which is perpendicular to the plane, and this is the point P which is on the plane. So given these two informations, given a point P and a vector q, I can define uniquely. So this plane is uniquely determined by P and Q. So uniquely determined means there is only one plane which contains point P and perpendicular to the vector q. There is no other plane in R3 which satisfies this condition, that containing the point P and perpendicular to q. So how to write down this vector? So let's say R कोई भी arbitrary point है plane के ऊपर. Okay, so this vector PR, this lies in the plane, and if it lies in the plane then it will be perpendicular to this vector q. So as you can see in this picture that if I have a line PR then it will be perpendicular to the vector q. So PR dot q must be equal to 0. So PR, the vector PR dot product with the vector q must be equal to 0, and this implies that R minus P dot Q is equal to 0, because what is PR? So let's calculate what is PR. So PR vector is equal to the position vector of R minus the position vector of P. So that's how you calculate a vector with initial point P and final point R. OR minus OP. So what is OR? This is R vector, and what is OP? So we can just say that the position vector of capital P is small p. So this is the position vector of P. So this is equal to R minus P dot Q is equal to 0. So that's how you define a plane in 3D. So इस चीज़ को हम यूज़ कर रहे होंगे. So in short, given a point on the plane and a vector perpendicular to the plane, I can define uniquely a plane in 3 space, and the equation of the plane is given by set of all points R such that R minus P dot Q is equal to 0, and this P and Q are given. So next thing which we are going to use in our lecture is Taylor series. Now what is Taylor series? So roughly speaking, if I have a function f of x which is infinitely differentiable, means इसका फर्स्ट डेरिवेटिव भी एग्जिस्ट कर रहा है, सेकंड भी, थर्ड, फोर्थ, अप टू सो ऑन, इसके तमाम के तमाम डेरिवेटिव्स एग्जिस्ट कर रहे हैं. Then the functional values of f of x near x is equal to 0. So for example, if I have a very small neighborhood of 0, so and x is any point inside this interval, so this interval is very small, very small interval. Then in the neighborhood of x is equal to 0, the functional values are given by f of 0 plus df by dx at 0 into x plus d square f by dx square at 0 into x square by 2 plus d cube f by dx cube at 0, x cube by 3 factorial plus up to so on. Infinite terms हैं इसमें, it's a series, और इस तमाम सीरीज का सम क्या है हमारे पास? दिस इज एफ ऑफ एक्स. नाउ द पॉइंट इज, अगर मैं इन तमाम इन्फिनिट टर्म्स में से कुछ फाइनाइट टर्म्स ले लूं, लेट्स से मैं फर्स्ट 10 टर्म्स ले लूं, देन इट विल नॉट बी इक्वल टू एफ ऑफ एक्स. देन वी कैन से दैट एफ ऑफ एक्स इज अप्रोक्सीमेटली इक्वल टू, लेट्स से मैं फर्स्ट 3 टर्म्स ले रहा हूं, सो एफ प्राइम ऑफ 0 इंटू एक्स plus f double prime of 0 into x square by 2 plus f triple prime of 0 into x cube by 3 factorial, and that's it. मैं अगर first 3 terms ले लूं, then I can say that f of x is approximately equal to this, और it's a relatively good approximation क्योंकि x is very small, और अगर कोई बहुत छोटा नंबर है और उसकी मैं जैसे जैसे पावर्स लूँगा, x is to power 4, 5, 6 अप टू सो ऑन, तो इसकी वैल्यू कम होती जाएगी. सो अगर मैंने फर्स्ट 3 टर्म्स ली हैं, इट्स स्टिल ए वेरी गुड अप्रोक्सीमेशन क्योंकि मैंने इंतहाई माइनर टर्म्स को इग्नोर किया क्योंकि x इज स्मॉल, सो x is to power 4 इज वेरी स्मॉल, x is to power 5 इज वेरी स्मॉल अप टू सो ऑन. सो मैं सिर्फ और सिर्फ जो छोटी टर्म्स हैं उनको इग्नोर कर रहा हूँ और जो बड़ी टर्म्स हैं वो मैंने लिख दी है. सो एफ ऑफ एक्स इज अप्रोक्सीमेटली इक्वल टू द सम ऑफ दीज फर्स्ट 3 टर्म्स. फॉर एग्जाम्पल, अगर मेरे पास साइन एक्स है, सो लेट्स से एफ ऑफ एक्स इज साइन एक्स. सो हाउ टू कैलकुलेट द टेलर सीरीज? सो व्हाट इज एफ प्राइम ऑफ एक्स? सो एफ प्राइम ऑफ एक्स इज इक्वल टू cosine x. What is f double prime of x? Is equal to minus sin x. What is f triple prime of x? Is equal to minus cosine x. Up to so on, हम सिर्फ first 3 terms calculate करते हैं. So let's say around 0 मैं टेलर सीरीज calculate कर रहा हूँ. So what is f of 0? So f of 0 is 0 in this case. F prime of 0 is 1 in this case. F double prime of 0 is 0 again, and f triple prime of 0 is minus 1 in this case. So इस terms में f of x के इस expression में इन terms को हम रखते हैं. So sin x equals to 0, f of 0 is 0, plus f prime of 0 into x, so plus x, f double prime 0 is 0, so दूसरी term यहाँ से 0 होगी, प्लस f triple prime is minus 1, so into minus 1 x cube by 3 factorial up to so on. So sin x is equal to x minus x cube by 3 factorial plus x is to power 5 by 5 factorial minus x is to power 7 by 7 factorial up to so on. So अगर आप कैलकुलेट करना चाहें तो आप इजीली कैलकुलेट कर सकते हैं. I can leave this as an exercise that this happens. Now if I take the first term, so if I just take this first term और बाकी तमाम टर्म्स को मैं इग्नोर कर दूं, then of course sin x is approximately equal to x, and it's a very bad approximation क्योंकि मैंने काफ़ी ज़्यादा टर्म्स को, काफ़ी ज़्यादा जो इम्पोर्टेंट टर्म्स थी x⁻3 x⁻5 और इन तमाम टर्म्स को मैंने इग्नोर कर दिया. सो एज यू कैन सी इन दिस पिक्चर कि ये sin x का ग्राफ है मेरे पास, ये जो बोल्ड लाइन है, बोल्ड रेड लाइन इज sin x, और इसमें ये जो ग्रीन लाइन है ये x है, y is equal to x. So this approximation and you can see that sin x का बिहेवियर और ग्राफ और है और इस लाइन का ग्राफ और है. लेकिन अगर मैं इसमें एक और टर्म ऐड कर लूं, -x³ / 3 सो एक और टर्म ऐड करने के बाद आप देख सकते हैं कि ग्राफ का जो बिहेवियर है वो चेंज होना शुरू हो जाएगा. सो इट बिकम्स दिस एंड इट्स मोर क्लोज टू साइन. सिमिलरली अगर मैं इसमें एक और टर्म ऐड कर लूं x⁵ / 5 then as you can see that it's more close to sin x. up to so on अगर मैं एक और टर्म ऐड कर लूं x⁷ 7 with a negative sign, then you can see that now it's very close. This term p7x, which is 1 2 3 4, the first 4 terms of the Taylor series of sin x, it is very close to sin x. So we can see that it's a very good approximation of sin x. So Taylor series is very good in approximating the functional values. Once again the same reason, क्योंकि x हमारे पास बहुत small है और अगर small है तो मैं higher powers को easily ignore कर सकता हूँ and it will not affect the functional value because for small x the higher powers are very small. So इस चीज़ को हम use करेंगे आज और ये देखेंगे कि Taylor series can be written in terms of the Frane frame, और अगर आपने उसको Frane frame में लिख लिया है then it is very useful and ये हम देखेंगे कि how it is useful. So what is the aim? So one of the aim of today's lecture is to approximate a curve near an arbitrary point on the curve. So कोई सी भी curve given है हमारे पास, हमने एक कोई सा एक point ले लेना. Let's say this is point on the curve. So this is point on the curve. और मुझे approximate करना है कि मैं exact curve को नहीं calculate करना चाह रहा. Exactness sometimes is not possible. बहुत ज़्यादा practical ऐसी situations हैं जिसमें exact value calculate करना या तो बहुत time taking होता है, आप इतना टाइम नहीं लगाना चाह रहे होते, या फिर यह कि impossible होता है. So it's always useful to approximate something. So इस केस में हम कर्व की जो पोजीशन है उसको अप्रोक्सीमेट करेंगे. सो लेट्स से ये जो रेड डॉट है मेरे पास ये कोई फंक्शनल वैल्यू है और मैं किसी वे से, किसी मेथड से ये पॉइंट फाइंड आउट करूंगा विच इज वेरी क्लोज टू दिस पॉइंट, और ये इस पॉइंट को मैं कहूंगा दिस इज अप्रोक्सीमेशन ऑफ द पॉइंट ऑन द कर्व. सो ये आज हम देखेंगे. सो हाउ टू डू दिस? सबसे पहले हमने टेलर सीरीज को देखा है, व्हाट इज टेलर सीरीज, और टेलर सीरीज को हम यूज करेंगे. उसके बाद फ्रेने फ्रेम एट ए पॉइंट को हम यूज करेंगे टू राइट डाउन द टेलर सीरीज इन टर्म्स ऑफ द फ्रेने फ्रेम, और डेफिनेटली फ्रेने फार्मूलाज भी हम यूज करेंगे. इन तमाम के कॉम्बिनेशन के साथ एट द एंड हमारे पास एक ऐसी टेलर सीरीज अप्रोक्सीमेशन आ जाएगी जो कि रिटर्न होगी इन टर्म्स ऑफ फ्रेने फ्रेम फील्ड. अब इसका फायदा क्या होगा? इसका एक सबसे बड़ा फायदा तो ये होगा कि वी कैन इन फैक्ट राइट डाउन द अप्रोक्सीमेशन इन टर्म्स ऑफ द थिंग दैट वी अंडरस्टैंड. सो वी अंडरस्टैंड व्हाट इज कर्वेचर, वी अंडरस्टैंड व्हाट इज टॉर्शन, एंड वी अंडरस्टैंड व्हाट इज नॉर्मल वेक्टर, बायनॉर्मल वेक्टर एंड टेंजेंट वेक्टर. सो वी अंडरस्टैंड ऑल ऑफ दीज क्वांटिटीज. सो अगर हमने टेलर सीरीज को लिख दिया इन टर्म्स ऑफ दीज ज्योमेट्रिक इंफॉर्मेशन अबाउट द कर्व, सो अप्रोक्सीमेट कर रहे हैं हम कर्व को इन टर्म्स ऑफ द ज्योमेट्रिक इंफॉर्मेशन ऑफ द कर्व. So what is geometric information? Again, this is torsion, curvature, normal, binormal, tangent, up to so on. So let's begin with the process. So इस ब्लू बॉक्स में आप देख सकते हैं हमने टेलर सीरीज जो अभी देखी है. Now let बीटा इज ए यूनिट स्पीड कर्व, जैसा कि मैंने लास्ट लेक्चर में भी कहा था, और आज का जो लेक्चर है इट्स ए कंटिन्यूएशन ऑफ द लास्ट लेक्चर. तो हम यूनिट स्पीड कर्व्स को डिस्कस कर रहे हैं. इसके बाद नेक्स्ट लेक्चर में हम ये देखेंगे कि हाउ वी कैन डू द सेम कैलकुलेशन, द सेम प्रोसेस फॉर arbitrary curves instead of just unit speed curves. So we can approximate each of the functions. Now we know that each of this function, beta 1, beta 2, beta 3, so these are functions. So beta I are functions from R to R. So these are real valued functions of one variable. So आपने देखा है कि जो टेलर सीरीज है वो भी फंक्शन ऑफ वन वेरिएबल की बात कर रही है. सो वी कैन easily apply the Taylor series on this beta i's. So what is the approximation without going into the detail of Taylor series again? So मैं easily लिख सकता हूँ, first three terms लिखी हैं मैंने Taylor series की, और what is the first term? f of 0, so beta I f 0. Second term is f prime 0 into s, so beta I prime 0 into s, so beta prime or d beta I by ds, so plus beta I double prime at 0 into s square by 2 plus d cube beta I by ds cube at 0 s cube by 3 factorial. So this is the approximate value of this real valued function. So we can do this thing for beta 1, beta 2 and beta 3. So now I can write down this beta as beta 1, beta 2, beta 3, and I can write down the approximation in the following way. So let's just write down the first two terms, and beta 1 of 0 plus beta 1 prime of 0 s plus, let's write down all of the terms. So to avoid confusion, we are writing down all of the terms, s square by 2 plus beta triple prime 0, beta 1 triple prime 0, s cube by 3 factorial. So this is the beta 1 part. Similarly, beta 2 0 plus beta 2 prime 0 into s plus beta 2 double prime 0 s square by 2 plus beta triple prime 0 s cube by 3 factorial, and plus the third part. So we can write down easily that this is equal to, so which means beta is equal to, so this is basically not exact value, this is approximate value, because I am approximating beta 1, beta 2 and beta 3 with this approximations. So this is approximately equal to, so beta 1 of 0, beta 2 of 0 and beta 3 of 0 plus s into beta 1 of 0 prime, beta 2 of 0 prime, beta 3 of 0 prime, plus the second terms s square by 2 beta 1 double prime of 0 plus beta 2 double prime of 0, sorry this is not plus, beta 3 triple prime of 0 plus up to so on. So I can write down in terms of these coordinate form. So what is this? This is beta of 0 plus s. What is this? This is beta prime of 0 plus, what is this? S square by 2. This is beta double prime of 0 up to so on. So एक third term last में आएगी आपके पास. So in coordinate form we can write down that this beta, which is equal to beta 1, beta 2, beta 3, is approximately equal to, we are not writing down it is exactly equal to, this is approximately equal to beta of 0 plus s beta prime of 0 plus s square by 2 beta double prime of 0 plus s cube by 3 factorial beta triple prime of 0, and that's it. We are just taking the first 4 terms of the Taylor series approximation of beta I. और फर्स्ट 4 टर्म्स हमने लिए हैं बीटा 1, बीटा 2, बीटा 3 के लिए, जो कि कोऑर्डिनेट्स हैं बीटा के, और उसके बाद हमने कोऑर्डिनेट्स में इनकी वैल्यूज पुट कर दी हैं, और जैसा कि हमने अभी देखा दैट दिस इज इक्वल टू दिस एक्सप्रेशन. सो बीटा एस is approximately equal to this curve. So this is also a curve because beta of 0 is a point in 3D, beta prime of 0 is a point in 3D, beta double prime of 0 is a point in 3D, beta triple prime of 0 is a point in 3D. इस तमाम को ऐड करेंगे you will get a point in 3D. So beta of s, which is a curve in space, is approximately equal to this curve. So this is not exactly equal to beta of s की approximation है ये. So let's say ये हमारे पास कोई curve है beta of s, then when you calculate these values beta of 0 plus s beta prime of 0 up to so on, ये इन expressions को calculate करेंगे जब आप, then it will give you a curve and it will be kind of approximation of the curve. So some point पे ये exactly equal होगी, some point पे ये नहीं होगी, और some point पे ये, so it will be something like this. So this is the approximation. And once again, why we do the approximation? Because sometimes it's not at all possible to calculate the curve exactly, and sometimes it's only required to calculate the approximate value. It's only useful, so we don't want to calculate the exact value. So approximation is always required in practical situations. So that's how we can approximate. This is the exact curve, and we can approximate it with this expression. Now we are going to understand what is this approximation. जैसा कि हमने शुरू में देखा sin x के एग्जाम्पल में, कि अगर मैं फर्स्ट 4 टर्म्स ले लूँ, first 4 non-zero terms ले लूँ, then it's a very good approximation of sin x. Similarly, these 3 terms, 4 terms are very good approximation of the curve. अब हम इस चीज़ को अंडरस्टैंड करने की कोशिश करते हैं कि अगर ये अच्छी approximation है कर्व की, तो इससे कर्व की जो ज्योमेट्रिकल प्रॉपर्टीज हैं वो कैसे डिराइव की जा सकती हैं, उनका इस अप्रोक्सीमेशन के साथ क्या रिलेशनशिप है. व्हाट इज कर्वेचर फ्रॉम हियर, व्हाट इज कर्वेचर, सो हाउ टू कैलकुलेट, हाउ टू डिसाइड curvature. Is it possible that we can decide the curvature of the curve from this approximation? Is it possible that we can find the torsion of the curve from this approximation of the curve? And is it possible to calculate tangent, normal and binormal of the curve from this approximation? So all the geometrical properties that we have studied so far, what are the relationships between those geometrical properties and this approximation of the curve? So that's our next target. So first हम इस चीज़ को लिखने की कोशिश करते हैं, इस approximation को लिखने की कोशिश करते हैं in terms of the frame field. So let's see. So this is just a reminder of the frame field. So as I said in my last lecture, it's always useful to remember this matrix instead of the Frene formulas. So in the first line, that's the approximation of the curve, or as we can see that given any point S, I will get an approximation. So it depends on S. So जैसे जैसे S चेंज होगा, कर्व के ऊपर पॉइंट्स चेंज होंगे, और ये अप्रोक्सीमेशन भी आप देख सकते हैं कि दिस डिपेंड्स ऑन S. So it's a curve with parameter S, which is approximation of the curve beta. So starting from the definition of the tangent, so what is tangent? So tangent is basically beta prime of S, and remember we are assuming that the curve is a unit speed curve, and if the curve is unit speed curve, in this case only beta prime is the tangent, and we will see in the next lecture that how it changes for the curves which are not unit speed curves. So this gives beta prime of 0 is equal to t of 0, and in short we can write it down as t of 0. So the value of the tangent at point S is equal to 0 can be written as t underscore t naught. Okay, so we can also write down t prime. So what is t prime? T prime by Frane formula. So from here t prime is equal to kappa into n. So kappa into n. And this implies, so what is t prime? T prime is basically beta double prime, because what is t? T is equal to, so t is equal to beta prime. What is t prime, sorry, what is t prime? This is equal to beta double prime. So this is equal to beta double prime is equal to kappa n s. So just मैंने t prime की जगह beta double prime रख दिया, because t prime is beta double prime. Okay, what is next? So next is beta double prime of 0 is equal to kappa of 0 into n of 0. So n of 0 means, so we know that this n is normal vector. What is normal vector? इसकी definition हमने last lecture में की थी, but we know that normal vector at a point gives me a vector, and normal vector can be calculated at each and every point on the curve. So it's a vector field on the curve. So normal vector field. So what is the normal vector at point S is equal to 0? This is n of 0. And if I change this value, if I change 0 to another point, let's say t or 100 or 10, it will give me another vector which is normal to the curve at another point. So this is the one of the vectors of the normal vector field. And so this is equal to beta naught double prime is equal to kappa 0. So once again kappa of 0 ko we are writing down in short kappa of 0 into n naught. So once again in short we are writing this down. So what we have got? So we have got beta prime of 0 is t naught. So let's write it down. So this is basically t naught. And what is beta prime? So beta prime we calculated, this is k naught, which is kappa naught, and n naught. Now what is left? This is the question mark now, and we are going to calculate what is beta triple prime of 0 in terms of the Frane frame field, or in terms of the Frane frame, and in terms of torsion and curvature and other geometrical properties of the curve we have studied so far. So to calculate beta double prime of 0, so we use Leibniz rule. So what is Leibniz rule? So Leibniz rule is, so we have seen that what is beta double prime. What is beta double prime? It's basically t prime. And what is t prime? This is equal to kappa n. So once again from this Frane formulas, t prime is equal to kappa n. Okay, so what is beta triple prime? So beta triple prime is equal to dt prime by ds, which is equal to dk kappa divided by ds. And using the product rule, or Leibniz rule, this is equal to dk by ds. And remember, this k depends on s. The curvature depends on the point. अगर point मैं different लूँगा तो मेरे पास curvature भी different आएगा curve का. और similarly जो normal vector है, it also depends on s. So for different value or different point on the curve, I will get a different value of n. So both of these quantities depends on s. So in the product rule, we will get d kappa by ds into n plus kappa dn by ds. And so by applying the Frenet formulas, we get n prime. So this is n prime. So n prime is equal to minus kappa t plus tau b. And if we write down this value in above formula, we will get, so this is n prime. So if we replace n prime with these values, we will get d kappa by ds into n. ये वैसे ही आ जाएगा हमारे पास. So this is the same as this. And kappa will remain here, and we will replace dn by ds by n prime s is equal to minus kt plus tau b. So अगर इसको multiply कर दें आप kappa के साथ, तो we will get minus kappa square t plus tau kappa b. So this is the value of beta triple prime of s. And in particular, what is beta triple prime of 0? In short, हम इसको लिख रहे हैं beta triple prime naught is equal to d kappa by ds at 0, n naught minus kappa naught square t naught plus t naught kappa naught b naught. So what is b naught? Binormal at s is equal to 0. Kappa naught is curvature at s is equal to 0. Torsion tau naught at s is equal to 0. Unitangent, curvature, normal, and the rate of change of curvature at s is equal to 0. तो ये तमाम वो informations है जो हमने already study की हुई हैं in the Frenet frame field और in the Frenet formulas. और अगर बीटा ट्रिपल प्राइम 0 की ये वैल्यू है तो इसको यहाँ पे हम पुट कर देते हैं. उसके बाद हमारे पास बीटा प्राइम 0, बीटा डबल प्राइम 0 और बीटा ट्रिपल प्राइम 0 की वैल्यूज आ गई हैं, वो यहाँ पुट कर देंगे हमारे पास. तो हमारे पास क्या आ जाएगा? सो व्हाट इज बीटा ऑफ एस? सो दिस इज इक्वल टू approximately equal to beta of 0, it remains the same, plus s into beta prime of 0, this is equal to s t naught, plus s into beta double prime of 0. So what is beta double prime of 0? This is equal to kappa naught n naught plus s cube by 3 factorial beta triple prime of 0. So this is equal to d kappa by ds at 0 n naught minus kappa naught square t naught plus tau naught kappa naught b naught. So अगर मैं इन तमाम वैल्यूज में t नॉट को कॉमन ले लूँ, n नॉट को कॉमन ले लूँ और फिर b नॉट को कॉमन ले लूँ, तो मेरे पास कुछ इस किस्म की वैल्यूज आ जाएंगी. So this is approximately equal to beta of 0 plus t naught. So what are the values of t naught? So s, और यहाँ से हमारे पास plus s cube by 3 factorial minus kappa naught square t naught. So that's the value t naught and that's the second value t naught जो हमने यहाँ पे लिखी है. Next we can write down the value of b naught. So इस टर्म में b naught नहीं है, इस टर्म में b naught नहीं है, so there is only one b naught, so it is s cube by 3 factorial tau naught kappa naught plus, so what are the values for n naught. So there is one coefficient of n naught here, so this is s squared by 2 kappa naught, and there is another over here plus s cubed by 3 factorial d kappa by ds at 0 whole multiplied by n naught. So once again there is a mistake, there is no t naught here. Okay, so that's the approximation of the curve beta of s in terms of t naught, b naught and n naught. और इसके जो कोएफिशिएंट्स हैं वो आप देख सकते हैं. इसमें s वेरिएबल है क्योंकि इट डिपेंड्स ऑन द वेरिएबल. जैसे जैसे s की वैल्यू चेंज करेंगे ये अप्रोक्सीमेशन आपके पास चेंज होगी. सो इट डिपेंड्स ऑन s एंड इट डिपेंड्स ऑन द कर्वेचर एंड टॉर्शन. सो कर्वेचर, टॉर्शन और टेंजेंट, नॉर्मल, बाई नॉर्मल की टर्म्स में हमने इस अप्रोक्सीमेशन को लिख दिया. नाउ देयर इज वन मोर इम्पोर्टेंट थिंग. वी हैव सीन दैट दिस s इज वेरी स्मॉल. सो जैसे जैसे हम किसी भी पॉइंट ऑन द कर्व पे हैं, लेट्स से, तो अगर दिस इज s इज इक्वल टू 0 पॉइंट ऑन द कर्व, और अगर मैं किसी भी नेबरहुड में हूँ, so let's say this is curve going on in like this is the point on the curve corresponding to s is equal to 0, or in other words this is beta of 0. So if s is very very small, so there is one point beta of s and we are approximating this value on the curve. So if s is very very small, then the powers of s, let's say s cube and other terms, they will be very very small. So हम क्या करते हैं, हम हर टर्म में से t नॉट के साथ जो कोएफिशिएंट है, इसमें जो हायर पावर की टर्म्स हैं उसको हम इग्नोर कर देते हैं. सो इस केस में फॉर एग्जांपल हम s क्यूब को इग्नोर कर देंगे. इस b नॉट के साथ सिर्फ एक टर्म आ रही है तो हम किसी को इग्नोर नहीं कर सकते. इस टर्म n नॉट में हमारे पास एक टर्म आ रही है s क्यूब के साथ, तो हम इसको इग्नोर कर देंगे. अगर इन दो टर्म्स को, सो वी इग्नोर दिस टर्म एंड वी इग्नोर दिस टर्म because these are higher powers of s, so we can easily ignore them and we get the following approximation of the curve. जो higher powers थी s की वो हमने ignore कर दी हैं और हमारे पास ये approximation आ गई है basically, and this approximation is called beta hat of s and is called Freinet approximation of beta near s. अभी तक हमने जो approximation की है वो s is equal to 0 के अराउंड है, and we can do basically this approximation for any point s naught other than s is equal to 0. and how do we do that? जो टेलर सीरीज है वो around any point s naught is given by f of x is equal to f of s naught plus f prime of s naught into s minus s naught, f double prime of s naught into s minus s naught square by 2 plus f triple prime of s naught into s minus s naught cube by 3 factorial up to so on. इसमें हम देख सकते हैं अगर s naught is equal to 0 put करें तो you will get the same Taylor series that we used earlier, and if we follow the same procedure that we followed, then you will see that the Freinet approximation of the curve at any point is given like this, and I am leaving this as an exercise. So क्या करेंगे आप, आपने इस टेलर सीरीज को यूज करना है और Freinet फार्मूलाज को यूज करना है. Freinet फार्मूलाज में कोई चेंज नहीं आएगी, जस्ट s इज इक्वल टू 0 की जगह आप s इज इक्वल टू s नॉट पुट करेंगे, और इस तमाम के बाद आपके पास जो Freinet अप्रोक्सीमेशन है कर्व की बीटा हैट ऑफ s नॉट is basically equal to this expression, and I'm leaving this as an exercise. So we don't need this S anymore, because so beta hat of S naught is basically beta hat of S naught. Okay, so now what is important? We have seen that at any point S naught we can approximate a curve. Now the important thing is, if I have a curve, let's say this trail is basically a curve, so let's assume, so we can assume that corresponding to every point on the curve I have a frame. So as you move along the curve, then you will have a frame and at each and every point on the curve, so till the end point. So this is the end point of the curve, which is the end point corresponding to the end point of the domain. So corresponding to every point on the curve, I have this frame TBN, I have the Frene frame, I have the Frene formula at each and every point, and I can approximate at each and every point the curve using the Frene approximation. So this is possible at each and every point on the curve. So for example, अगर मेरे पास कोई सी भी curve given है 3 dimension में, so let's say this is a curve in 3 dimensions, then as I move, so this t is basically the parameter. So as I move the values of t, I'll be moving along the curve. So जैसे जैसे मैं t की values को increase करूँगा, I'll be moving along the curve. और जैसा कि आप देख सकते हैं, as I'm moving along the curve, I'm getting this normal vector, tangent vector and binormal vector as I move across this curve. And so I can do the same computations जो कि हमने की हैं किसी भी point S naught के लिए. I can do the same computations at each and every point on the curve. So I can approximate each and every point of the curve. So I can use this scale to increase the size of this frame, and I can also increase the size of the curve. So this is important. So this file will be available with the lecture notes. So all you need to do is install this software called CDF Player, and once you install the software, then you can easily open this file, and basically you can use these commands to see for yourself how moving along the curve you will get a frame at each and every point of the curve. And this software CDF Player is also available online for free at the Wolfram Mathematica website. So what we have done so far? So we have done the following. Corresponding to every point on the curve, I can approximate the value of the curve corresponding to that point. So हमने जो computations की थी शुरू में वो s is equal to 0 के लिए थी. उसके बाद फिर हमने कहा कि if a point is in the neighborhood of any point on the curve s naught, then I can do the same computations, and since corresponding to every point on the curve there is a tangent, normal and binormal, so there is a frame field at each and every point on the curve. So that is why I can approximate, and I can write down the approximation corresponding to every point in terms of the tangent, binormal, normal vectors, torsion and curvature. So अभी तक हमने approximate किया है curve को in terms of these geometrical properties of the curves. So अब हम देखते हैं कि इस approximation का meaning क्या है. So let's consider this approximation, this beta hat is approximation of the curve near s is equal to 0. So we can see that this is 0, so this is the approximation of the curve near s is equal to 0. So s is a point very very close to 0. So let's say मैं सिर्फ और सिर्फ first two terms को consider करता हूँ. So let's consider the Freinet approximation, which is very very rough approximation, क्योंकि मैं इसको ignore कर देता हूँ और third term है इसको भी ignore कर रहा हूँ. So let's consider for a moment that we are ignoring the last two terms and we are just writing down the first two terms. Now what is beta of 0? It's a point on the curve. So this is beta of 0. So this is the curve beta, and this point is basically beta of 0. It's a point on the curve. What is s? It's a variable, it's a parameter. And what is t naught? T naught is basically tangent to the curve at point beta of 0. So in this picture we can see that it will be a unit vector in the direction of this t naught. So this basically is t naught vector. It's a unit vector in the direction of tangent. So what happens if I multiply t naught with a number? So multiplying, so basically s is a number. So if I multiply s with this t naught, which is a vector, I will get a vector which is basically either it's greater in the length to t naught or it is less in the length to t naught. So दोनों में से कोई एक बात हो सकती है depending on the value of s. So I will get this s t naught. So let's say this vector is s t naught. So the length here to here is the length of the vector s t naught. And so अगर हम रिवाइज करें, हमने लाइन की इक्वेशन फाइंड आउट की थी. इसमें b naught is a fixed point, t naught is a fixed vector, and s is parameter. So this is parameter. So if you remember, what is the equation of a line passing through a point and parallel to vector q? It was the same as p plus qt, and this t is the parameter. It's very similar to this. And so what is this expression? If I ignore the last two terms, the first two terms will give me a line passing through point beta of 0 and parallel to the tangent vector, in fact unit tangent vector. And so the approximation of the curve at point s, which is very close to, sorry, this is point s, at point s, which is very close to 0, is in fact a straight line. And what is this? The straight line can be calculated from b of 0 plus s t naught. So that's how you calculate this straight line, which is the very rough approximation of the curve near the point s is equal to 0. So the curve defined by s goes to beta of 0 plus s t naught is the tangent line to beta at s is equal to 0. So basically it's not unit tangent vector, it's the tangent line, which means it is a line containing point beta of 0 and is parallel to the unit tangent vector. So that is tangent line. It is the best linear approximation to beta near beta of 0. So near beta of 0 means, once again, a point which is very very close to s is equal to 0. S is a point very very close to s is equal to 0, और इस point पे beta of s की जो approximation है, linear approximation, वो हमारे पास क्या आ रही है? Beta of 0 plus s t naught. अब इसको लीनियर अप्रोक्सीमेशन हम क्यों कह रहे हैं? क्योंकि इसमें s की पावर 2 और 3 और हायर पावर्स नहीं आ रही, सो इट्स ए लीनियर फंक्शन। इसमें s की या पैरामीटर की जितनी भी पावर्स हैं वो 1 है, इसमें 2 या 3 या हायर पावर्स नहीं आ रही, सो इट्स ए लीनियर अप्रोक्सीमेशन of this curve beta near s is equal to 0. Next हम देखते हैं कि if I ignore the last term and just consider the first three terms, then what is this geometrically? So geometrically this is a quadratic function, a function involving 1 and 2 powers of the parameter. So it's a quadratic function, and in particular it defines a parabola. So if you remember that if you consider a function like ax plus bx square plus c, then it gives me a parabola in plane, and this is basically a parabola in which plane? A plane decided by t naught and n naught. So what is t naught here? So t naught is given here, and what is n naught? N naught is given here. And what is the plane that we are talking about? So this is the plane. So इस plane की बात हो रही है, decided by or defined by t naught and n naught. इस plane में ये जो approximation है curve beta of s की with this quadratic function is a parabola, and this plane decided by t naught and n naught is basically called oscillating plane, and this parabola will something like this, and this will be contained in this plane. Okay, so that is the approximation of the curve when you only consider the first three terms and ignore the last term. This is basically a parabola contained in the oscillating plane. Now let's see what are plane curves. अभी हमने parabola की बात की which is contained in the plane. What are the curves which are not contained in the plane? So this is example of a curve which cannot be contained in the plane. So it is curved in space in such a way that there is no plane containing this curve. And we also know that helix is also one of the examples of the curve which cannot be contained in a plane. So it's not a planar curve. So what is a planar curve? A curve which is contained in a plane in R3 is called a planar curve. And once again, going back, this parabola is a planar curve which is contained in the oscillating plane. So this approximation of the curve by just considering the first three terms of the Frenet approximation and ignoring the last term is basically a parabola in the oscillating plane, and it's a planar curve. Now let's see what happens if I consider all of the terms. So ignoring the rest of the terms, so we are ignoring these terms and just consider these terms. Okay, then the approximation is a curve which is moving the parabola in the third dimension. Now let's see, as we have seen that this is the oscillating plane. So in this oscillating plane, the approximation, if I consider the first three terms, it's a parabola. So as I said, that it is something like this. Now what happens if I consider this term, the term containing the third power of s and also containing b naught? So this b naught is important because we are now considering the third dimension. So before that we were only considering t naught and n naught. So the curve was, that's why the curve was contained, the approximation of the curve was contained in the plane. Now we have the third dimension. b naught is a vector. इससे आप किसी नंबर को tau naught, kappa naught, s cube by 3, ये एक नंबर है, इसको b naught से मल्टीप्लाई करेंगे और उसका इफेक्ट भी आएगा. सो बेसिकली आप इसको लिफ्ट कर रहे हैं. सो इस कर्व को आप लिफ्ट कर रहे हैं, यूं समझ लें आप इसको मूव कर रहे हैं. इस पॉइंट से पकड़ के अगर आप इसको लिफ्ट करें तो आपके पास ये अप्रोक्सीमेशन आ जाएगी विच इज गिवन ओवर हियर. सो दिस इज बीटा हैट ऑफ s with all the four terms taken. So what is this approximation? So this point beta hat of s is the approximation of beta of s. So we don't know where is the curve. So maybe the curve is somewhere going like this, very very close to this point. So we don't know. So maybe this is the actual curve. So this is the actual curve, but this is, you can see that this is beta of s, and this is very very close to beta hat of s, and so this is the approximation of the curve. So that's what it means, that if you approximate a curve by Taylor series and then write it down in terms of the Fresnel frame and use the Fresnel frame formulas, and then you see that it is in fact given like this. Now the next thing is, we have seen that what is a planar curve. A planar curve is a curve which is contained in a plane in 3D. And what is a curve which is not a planar curve? Which cannot be contained in a plane. So this is a planar curve, as it is basically tilted, but we can easily find a plane. We can easily find a plane containing this curve. So it is a planar curve, and it is not a planar curve. But how we can decide that a curve is planar curve or a curve is not a planar curve? Because we have asserted that अभी तक जो हमने properties calculate की हैं, torsion, curvature, normal, tangent and binormal, ये तमाम की तमाम curve की geometry को express करती हैं. So is it possible कि मैं in terms of these notions मैं इस चीज़ को express कर सकूं कि कब curve planar होगी और कब curve planar नहीं होगी? And the answer is yes, it is possible. I can write down the following statement. So let beta be a curve in R3 with positive curvature. So this thing is important. So we are only ignoring one case with curvature equal to 0, and we have seen that when kappa is equal to 0, if and only if beta is line. So I am leaving this as an exercise. You can easily prove that this is possible. If k is 0, then b is a line. So we are just ignoring the line case, and we are assuming that kappa is greater than 0. Then beta is a plane curve if and only if torsion of the curve is 0. So basically the torsion calculates, or torsion measures the amount in which the curve is not planar. So अगर torsion 0 है तो ये curve totally plane में contained है. अगर torsion थोड़ा सा कम है तो planar तो नहीं है लेकिन close to planar curve है. और अगर torsion बहुत ज़्यादा, then the curve is very very not planar. In other words, it's very very far from contained in a plane. So let's prove this statement, that let beta be a curve in R3 with positive curvature, then beta is a plane curve if and only if torsion is 0. So there is if and only if involved here. So let's first assume that beta is plane curve, and we will prove that. So to prove is torsion is equal to 0. And how to prove that torsion is equal to 0? And since beta is a plane curve, so it is contained in this plane, then there exists a point P and a vector Q. So this implies there exists point P on plane and vector Q perpendicular to plane such that beta of S minus P is perpendicular to Q. Now P and Q are fixed and their derivative is 0, and beta of S is not fixed, it's a variable quantity, and its derivative will not be equal to 0. So differentiating will give us beta prime of S, the derivative of P0 dot Q plus beta of S dot Q prime, and this is equal to 0, but we know that this is basically 0. So what we get? So we get that beta prime of S dot Q is 0, and this implies that tangent vector. So what is beta prime? If beta is a unit speed curve, then it is tangent vector, unit tangent vector. So that's the first thing we get. Secondly, differentiating again. So differentiating again, we get beta double prime S dot Q is equal to 0, and we can divide it. Since the curvature is greater than 0, I can divide it by curvature and dot equal to 0, and this implies that N dot Q is equal to 0. So the point is, this Q is perpendicular to both N and T, and if there is this Q and it is perpendicular to both N and T, and we also know that T cross N is a vector which is perpendicular to both T and N, then we can see that, so this implies that the binormal vector, which is T cross N, is basically parallel to the vector Q, and so this implies that B is equal to Q divided by norm of Q, because Q may or may not be unit, so we normalize it and make it a unit vector, and so this implies that beta prime is 0, and if beta prime is 0, then we know that beta prime is equal to torsion N, and this implies that torsion is equal to 0 because N cannot be equal to 0. So next, let's see how to prove the converse of the statement. So what is the converse of the statement? If the torsion of the curve is 0, then we have to show that, so to show is it is a plane curve. So if torsion is 0, then this implies that B prime, which is equal to minus tau n, so B prime is 0. Now consider we have a trick to prove this part. So we consider a function f of s which is equal to beta of s minus beta of 0 dot b, और basically अगर हम ये show कर दें that f of s is 0, then this will imply that beta of s minus beta of 0 dot b is 0, and this implies that beta of s is always contained in a space which is perpendicular to the binormal vector. So this implies beta of s is contained in plane perpendicular to B and containing B of 0. So if we can show that, then we are done. Now what is f prime? So f prime of s is equal to beta prime of s dot b. What is beta prime of s? This is t dot b is equal to 0, and we also know that f of 0 is 0. So यहाँ पे अगर आप 0 रखें तो beta of 0 minus beta of 0 0 हो जाएगा. So f of 0 is 0, and this implies that f of s is 0, and basically if you integrate this function and f of 0 is 0, then we can use that the integral of this f prime of s is equal to 0 is a constant, but since f of 0 is 0, so f of s is 0. So I am leaving this step as an exercise. And so this implies that beta of s minus beta of 0 dot p is equal to 0, and so the curve is planar curve. So what is torsion? Torsion gives you measure of how much a curve is not planar. If torsion is 0, then it is a plane curve, and if torsion is non-zero, then it is not a planar curve, and if torsion is higher, then the curve is bending too much in space and it's very far from being a plane curve. So next time we will be continuing this Fresnel approximation, and there will be 1 or 2 more results in interpreting this Fresnel approximation and to determine how the geometrical properties can be obtained from this Fresnel approximation. And we will also start the new topic called the arbitrary speed curves. As a matter of fact, we will be translating the whole geometrical discussion of the curve from unit speed curves to in general curves. So हमने पिछले 2 लेक्चर से ये चीज़ अज्यूम की हुई है कि हमारे पास जो कर्व्स हैं वो यूनिट स्पीड कर्व्स हैं, लेकिन इस सेक्शन में आर्बिट्रेरी स्पीड कर्व्स के अब हम ये अजम्पशन ड्रॉप कर देंगे और तमाम की तमाम प्रॉपर्टीज़ को डिस्कस करेंगे फॉर जनरल कर्व्स. This is the end of the lecture. Thank you very much and Allah Hafiz.